All right, now this paper that we're looking at, this one is now 2017 Pure Mathematics Unit 2. And we're, of course, we're looking at the integration questions continued, and it says, use integration by parts to derive the reduction formula that a times in is equal to e to the ax minus n times in minus 1. Now, before we even do this question, I noticed that we're going to get some in minus 1. And I just want to remind again that if in is the integral of x to the n, then in minus 1 is going to be equal to, it's going to be the integral of x, and instead of the power n, it's going to be n minus 1 times e to the ax. So I just wanted to point out that this is in minus 1. So replace n with n minus 1. So now let us go ahead and tackle this question. So to tackle this question, the first thing we want to start with is to integrate this is integration by parts, and we need to remember ILATE rule. ILATE tells us that algebra comes before exponential functions. Algebra comes before exponential functions. So what that is telling us is that this exponential function is going to be our dv, and this x to the n is going to be our u. So let's do this real quick. Easy question. So we'll start with now in. So in is going to be equal to, I'm going to write u up here. We're going to call u is x to the n. U is x to the n. U is x to the n. And so du is the differential of x to the n. And so to differentiate x to the n, we carry down the power and we subtract 1 from the power. All right, and that's du. And then dv is going to be e to the ax. And so in order to get v, we're going to have to integrate e to the ax. And that's not too bad. So let's integrate this to get v. When we integrate this, what we're going to get is e to the ax, and then we're going to divide it by a. So it's e to the ax being divided by a. So that's the v. All right. And so now what we need to work out is, of course, u times v. So to work out u times v, it's going to be in is uv minus v du. So u times v is going to be 1 over a x to the n, 1 over a x to the n, e to the ax. It's 1 over ax to the n, e to the ax minus v du, which is minus the integral of v du. V du is going to be, this looks like n over a times n to the x minus 1. Well, we already wrote down the n over a, so it's times x to the n minus 1 times e to the ax dx. So this question is so easy. Then all we're required to do now is to multiply in by a. So when we're going to multiply in by a, what we're going to get is in, we multiply it by a, it's going to be equal to a over a, that gone, so it's then going to become x to the n, e to the ax. Multiplying by a now becomes an over a. Then the a cancels the a, so we'll get minus. We can factor out the n as well and write n times the integral of x to the n minus 1 e to the ax dx, of course. All right. But now look at this now. We're nice, you know, we're really nice. We're straight. Because look at this now. X to the n minus 1 e to the ax is in minus 1. So what we get is a times in, and that's equal to x to the n e to the ax, x to the n e to the ax minus n times in minus 1. All right, and that's that. All right, easy question. Soft with a capital T. Soft. All right. Now the next part of this question, it says hence determine, hence or otherwise, meaning we don't necessarily have to use this. Hence or otherwise, we're going to be working out the integral of x cubed e to the 3x dx. So in order to work out this question now, what we're going to do is we're going to substitute right here. We're going to substitute x to the n it was, right? X to the n, so we're going to substitute n equal 3 and a equal 3. All right? So that's what we're trying to find. And it says hence, meaning use this result. We're going to use this result. All right? So what we're going to do is we're going to let a equal 3. So there's a reduction formula. We're going to let a equal 3. Let a be equal to 3 and n be 3. If a is 3 and n is 3, then what we're going to be getting is a is 3, so we're going to get 3 times I3, 3 times I3, and remember I3 is this thing right here. This is I3. So 3 times I3 is equal to x to the n, which is x to the n, and n is 3, so it's x cubed e to the ax, which is e to the 3x, minus n times in minus 1. Now in minus 1 is minus n, which is 3 times in minus 1. In minus 1 is 3 minus 1, and 3 minus 1 is 2. So we get minus 3 times I2. Nice. Now you see what's going on? Yes, lovely. So now catch the pre now. We can find 3I2 now. So we're going to have to find 3I2 now. So let's find 3I2. Let's put it in black. So we're going to put 3I2 in black. So to find 3I2 is going to be equal to, because remember A is still 3, so 3I2 is going to be equal to, now in this case now, n is 2. N is 2 and A is 3, so it's going to be x squared. This looks like x squared e to the 3x, x squared e to the 3x, minus x squared e to the 3x, minus, you're wondering why did I write it so far over? Because I'm going to substitute this right here. All right, so I2 is equal to x squared e to the 3x minus n in this case is 2. 2 times 2 minus 1. 2 minus 1 is 1. Nice. So look how almost good so far. So I'm going to substitute this. I'm going to substitute all of this. in this. I'm going to substitute in this. And so what I'm pretty much saying is that 3i3 now, 3i3 in reality is equal to x cubed e to the 3x, x cubed e to the 3x minus, now it's minus all of this that we have over here. So it's minus x squared minus x squared e to the 3x. But then the minus, when we're subtracting all of this, the minus and the minus make this become plus. It become plus 2i1. So now we're going to need to work out what is I1. What is I1? Let's go ahead and work out I1 for ourselves now. So to work out I1, again, I'm going to do it in black. And so the reality is 3i1, meaning A is 3 and N is 1. 3i1 is equal to, substitute N as 1. N is now 1, so it's x to the 1 times e raised to the ax. A is 3, so x e to the x minus n is 1, so that's 1 I to the 1 minus 1. That's really I naught. So that's I naught. All right. But now what is I naught? So I'm going to put where I naught is when n equals 0. I naught is equal to, that means n is 0. So it's equal to the integral of I naught is n is 0. So going back to the original formula, x to the n, e to the ax. So I naught is equal to x to the n, but n is 0. So it's x to the 0, e to the 3x. That's I naught dx. Anything to the 0 is 1, and so this becomes integrating e to the 3x, and integrating e to the 3x is e to the 3x over 3. All right, so now we can substitute all of this for I1. All right, so we can substitute all of this for I1. So I1, in reality, what is I1? I'm just going to plug in this e to the 3x right here. And so I1 is really x e to the 3x minus e to the 3x over 3. But look at this now. This is now 3i1, but let's say I just want I1. I1, I'm going to divide through by 3, and dividing through by 3, I get x e to the 3x divided by 3 times 3 is 9. So this is now I1. I1 is x e to the 3x over 3 minus e to the 3x over 9. So that is I1. Now I'm going to plug all of this weird stuff right here. I'm going to plug it into right here. So now for I1. So now we're almost finished. Come on, finish strong. So 3i3 is equal to, 3i3 is equal to, that looks like x cubed e to the 3x, x cubed e to the 3x minus x squared e to the 3x, x squared e to the 3x plus 2 times I1. So it is plus 2 times I1, which is 2x e to the 3x over 3 minus 2 times e to the 3x over now 2 over 9 plus some constant c. But no, this is 3i3. All right, this is 3i3. We just want i3. So because we just want i3, all we're required now to do is just divide through by 3. So let's go ahead and just divide through by 3. So to divide through by 3, what we're going to get is i3 is equal to dividing through by 3. We get 1 over 3 x cubed e to the 3x, 1 over 3x cubed, e to the 3x, minus 1 over 3 x squared, minus 1 over 3 x squared, e to the 3x, and then plus, or divide through by 3, we're getting 2 over 9 x e to the 3x, 2 over 9 x e to the 3x, and then we divide through by 3 right here to get minus, now I'm just gonna push up this 3 so it don't look like it is in this line. I want to push up this 3. So divide through by this 3 to get 3 times 3 is 3 times 3 times 3 is 27. So it's 2 over 27 e to the 3x plus c. All right, and that's the answer. Soft. So just a recap of this question, just a full recap, right? We want to show that, all right, let's zoom in a little. We want to show that in, which is equal to x to the n e to the ax. We need to show that ain is equal to x to the n e to the ax minus n times in minus 1. To do this, we had to use integration by parts. And to do integration by parts, we have to remember the Euler's rule. And using the Euler's rule, we substitute u as x to the n and dv as e to the ax. So we find du and v, and then remember that the integral of u dv is equal to uv minus the integral of v du. And so doing that, it simplifies out, and then we multiply through by a, and we get the result. All right, so that's very easy. The next part now, we're otherwise determine x cubed e to the 3x. Now, if you look at the reduction formula, you can go with the hence, and you know that ain is equal to x to the n e to the ax minus n times in minus 1. In this case, right, in is the integral of x to the n e to the ax. If we replace n with 3, we get i3 is x to the 3, and in this case a is 3. So in this case a is 3 and n is 3. So what we're finding is I cube. But since a is 3, we can say that 3i cube is x cubed e to the 3x minus 3i squared. Following the reduction formula, we just plug in a as 3 and n as 3, and then it becomes x cubed e to the 3x minus 3i 3 minus 1, which is i2. Now, after we do that, now we're trying to find I cube, we're trying to find I3. So what we're going to then do is we need to continue with the reduction formula to find I2. But we know that 3I2 would be equal to x squared e to the 3x minus 2I1. So then we know can plug all of this now for 3i2 right here. It's going to be minus all of this. So plug that here to get this. So now we just need to get I1. So we just need to get I1 and we plug in A as 3 and N as 1 and we get 3I1. So make I1 the subject and plug it here. All right. But I0 is very easy to find because I0 is when N is 0 and anything to the 0 is 1. So we're just integrating e to the 3x, which is e to the 3x over 3. So again, we get 3i3 is now equal to, we substitute for I0, I1, I2, everything we substitute back into the formula for I3, and we get this long equation. But then this is now 3i3, so divide through by 3 to get this is what I3 is equal to. Now to confirm your answer, I always say, check it with Symbolab. Let's see if this is the same thing we got. I am 99% confident that we are fine. And so let's check it with Symbolab. It's a wonderful app to check your answers with. And so that's what we're about to do. We're about to check with Symbolab. So let's check it. So we're going to check with Symbolab and we're going to check to see if the integral of x cubed times e raised to the ax, in this case e to the 3x, dx, it should give us all that long stuff that we got. So let's see. 99% confident that we're fine. Unless it's, all right. So here it is. It's 1 over 27 e cubed into 9x cubed minus 9x squared plus 6x minus 2. So we're pretty much good. If we factorize out 1 over 27 e to the 3x, we'll get the same answer. So we could factor out 1 over 27. If we had to factor out 1 over 27, if we factor out 1 over 27 e to the 3x, factoring out 1 over 27, we'll leave the 9 here. Factoring out 1 over 27, we'll leave, yeah, we would get it. Factoring out 1 over 27, we leave the minus 2. So just need to factor out 1 over 27 e to the 3x. If you want your answer to look pretty, then you'll have the x cubed, the minus the x squared plus the x. It will look pretty if you factor out 1 over 27 e to the 3x. But I'm not about that pretty stuff right now. So we leave it right here. And so this takes care of the first part of 2017. Integration is so nice and easy. Say it with me. Integration is so nice and easy. All right. Now we're going to look at this question. Now this question asks us to evaluate. This must be 2 marks because this is so easy. A whole of 5 marks. They're giving it away. Now the integral of sine inverse divided by 1 minus x squared. Now think about it this way. If u is equal to sine inverse of x, what is du? Right? That's all you're doing, you know. This is so easy. Like, look at this. This is now integration by substitution. Right? Because if u was equal to sine inverse, if u is equal to sine inverse of x, right? Then what would be du? When we differentiate u, what we get is du is equal to differentiating sine inverse is 1 over the square root of 1 minus x squared. So get 1 over the square root of 1 minus x squared dx, right? But no, we're not finished yet. We need to talk about the upper limit and the lower limit. Now the upper limit that we're gonna get is we need to plug in when x is 1, what would we get? Sine inverse of 1. We always have to change the limit. So plugging in x is 1. So my calculator, plugging in 1, we get the sine inverse of 1. And the sine, I can't believe I didn't remember that. Sine inverse of 1. Sine inverse of 1 is pi by 2. That's pretty shameful to not remember pi by 2. But that's pretty bad. And the lower limit is when we plug in 0, sine inverse of 0 is 0. Sine inverse of 0 is 0. And so now we can substitute. And so all of that becomes equal to the integral of, we're plugging u as sine inverse. And so what we're integrating is from 0 to pi by 2. We're integrating from 0 to pi by 2 of u du. So easy. So integrating u du, what we're getting is u squared over 2. And we're integrating that from 0 to pi by 2. Integrating this from 0 to pi by 2. Nice and easy. Soft. So all I do is plug in pi by 2 right here to get pi by 2 all square over 2, pi by 2 all square over 2, minus, when we plug in 0, that's just 0. So pi by 2 all square over 2, that looks like pi square over 8. That's the final answer I'm getting, pi square over 8. Pi square over 8. Yeah, 2 square 4, and dividing by 2 is multiplying by a half. So pi square over 8 is the final answer. So this works out to be pi square over 8. Easy, soft, with a capital T. Soft. All right. So just to check this answer, we go to Symbolab. Again, I'm always showing you this, guys, just to get used to practicing, making sure your answer is correct. So the integral from 0 to 1 of what that thing was again, sine inverse. That's sine inverse of x over the square root of 1 minus x squared. All right, and you check your answer, and let's see what we get. Should get pi square over 8. I'm confident. There it is, pi square over 8. And so we're good. Pi square over 8. We're absolutely fine. We're absolutely fine. So integration is so nice and easy. Say it with me. Integration is so nice and easy. Say it with me. Integration is so nice and easy. It's so nice and easy. Integration is so nice and easy. All right. So we have one more integration on this piece of paper from 2017. And so in this case, what they're asking us to do is to use partial fraction to show that 2x squared minus x plus 4 times x cubed plus 4x is equal to 1 over x plus x over x squared plus 4 minus 1 over x squared plus 4. Okay, so to use partial fraction to show that, let's do it. Don't see why they want to complicate it. Well, let's see. To do this using partial fraction, obviously we realize that in the denominator, it has a highest common factor of x can be factored out, so we can write it as 2x squared minus x plus 4, and all of that is divided by, we can always factor out x, and so by factoring x, we get x times x squared plus 4. Easy. So this is the easy part out of the way so far. Now, this quadratic is irreducible. And so since it's irreducible, the type of partial fraction it's going to be separated in is a over x plus bx plus c. So it's a over x plus bx plus c, bx plus c over x squared plus 4. That's what we're going to get over x squared plus 4. Now that's what we're going to get. Now when it gets to this stage now, it's very easy. We just need LCM. So find one big LCM of everything. So let's do that. One big LCM. One big LCM of everything is x times x squared plus 4. So x times x squared plus 4. And so now we'll say all of this right here into this, leaves back this up here. So we're getting our 2x squared minus x plus 4. And that is equal to x into this leaves a times x squared plus 4, a times x squared plus 4. And then b into this, or x squared plus 4 into this leaves just x. And so it's bx plus c times x. So I'm just going to write bx squared. Since it's multiplied by x, I'm just going to write bx squared plus cx. Now, since whenever you have two fractions and their denominator is the same, we can just go ahead and equate the numerator. So we can just go ahead and equate the numerator. And so by equating the numerator, what we're virtually saying is 2x squared minus x, 2x squared minus x plus 4, 2x squared minus x plus 4, we're virtually saying that this is, of course, equal to ax squared, this is equal to ax squared plus 4a, it's equal to ax squared plus 4a plus bx squared plus cx. This is virtually what we're saying. Nice. So this is what it's equal to, plus c times x. Now, once we get to this stage, what we're going to be doing is equating coefficients. So 2x squared, and we have ax plus bx squared. So what we're virtually saying is the coefficient of x squared on the left-hand side is 2. The coefficient of x squared on the right side is a plus b. So 2 is equal to a plus b. Easy. Then the coefficient of x is negative 1 on the left. And so negative 1 is equal to, look for the coefficient of x on the right-hand side. And apparently it's just c. And so c is going to be negative 1, which makes it a lot better. And then 4 is our constant. And the constant that we have right here is 4a. And so what we're saying is 4 is equal to 4a. Now if 4 is equal to 4a, then it implies that a is equal to 1. A is equal to 1. Now follow the loop. Now if a is equal to 1, this implies that 2 is equal to 1 plus 1, because a is now 1. 2 is equal to 1 plus 1, so b must be 1. So b must equal 1. So a equal 1, b equal 1, and c equal negative 1. And so guys, we're exceptional now, we're really nice. So virtually, what we're saying now is we'll finally finish. So we can conclude now that 2x squared minus x, 2x squared minus x plus 4, and all of this is being divided by x times x squared plus 4. All of this is divided by x squared, x times x squared plus 4. So we have this, and this is equal to we said that it was a over x, so it is 1 over x plus bx plus c, bx, now bx, where is bx? So it is bx, which is 1x, so it is now bx plus c, so it's bx minus 1 over x squared plus 4. Now, this is not what the question wanted to show. Now, we can separate this even some more. We can separate this fraction into the sum of two partial fractions. So we can write it as x over this minus 1 over this, right? So that part can be broken down even some more to say that this is now equal to 1 over x. Catch the pre now, you know, catch a pre. Yo, catch a pre. X over x squared plus 4. So it is plus x over x squared plus 4. Easy. X over x squared plus 4. And then we write it as minus 1 over x squared plus 4. And that's how we separate that as partial fraction. All right. Very, very, very easy. Soft with a capital T. Soft. Soft. Softy, softy, softy. Very easy. Very, very, very easy. Almost too easy. All right, soft. Now, it says hence or otherwise. Otherwise meaning you can use some other alternate method to integrate this right here. But it says hence, I would mostly go for hence. You could use otherwise by saying the differential of 3x. Differential of x cubed is 3x squared. Differential of 4x is 4, but then you'd have to counter for the minus x. You still have to separate it. You could use other methods, but I'm going to go with the hence. Hence meaning, given that we know, so this is what we do know. We do know that 2x squared minus x plus 4 over x cubed plus 4x. We do know that this can be separated as the sum of 3 partial fractions, right? So since we can separate this as the sum of 3 partial fractions, we're just going to integrate those 3 partial fractions. So this, as we said, we found that it's equal to 1 over x plus 1 over x squared plus 4 plus 1 over x squared plus 4 minus 1 over minus 1 over x squared. Oh, this is 1x. This was plus 1x. So I'm just going to write x minus 1 over x squared plus 4. So now, since we know this partial fraction, then what am I saying is, now students, don't leave off your dx, but in my case, I'm going to leave it off. The integral of all of this is going to be equal to the integral of all of this, which is just the integral of 1 over x plus the integral of x over that minus the integral of this. That's what we know now. That's why I said the hence is better. So this now works out to be the integral of 1 over x is ln x. I like to put ln mod x just to show some respect that we know x can't be negative. Plus, now to integrate this now the differential of the denominator is in the numerator, but we need a 2 right here. So we're going to put a 2 right here and put a half on the outside. We put a 2 right there and then put a half on the outside, right? So we don't change the value, because if we put a 2 right here and a half on the outside, we're nice, right? So now that the differential of the denominator is in the numerator, it becomes a half ln the denominator. So it becomes a half ln the denominator. A half ln x squared plus 4. And then we minus. Now we'll have x squared plus 4 right here. So this look like tan. This look like tan inverse x over a. So it's tan inverse x over 2. So it's minus tan inverse, this is tan, minus tan inverse x over 2. All right, and so that's the answer. Of course, you can put plus your constant of integration. So just to finish, you can just put plus k. Right? Easy, soft. This question was so soft. Softy, wafty, wafty. Look at that. I can't 5 marks this. Too easy. They're giving away 5 marks. They're giving it away. You write soft with a capital T. So the answer is ln. Now this is just ln mod x plus a half ln the modulus of x squared plus 4 minus tan inverse x over 2. A lot of people won't put modulus, right? But I like to put modulus just to show respect that we can't take ln of numbers that are going to be less than 0, right? Log of a negative number does not exist. So just to put some respect on the log. And again, you can check it. Just check that you're going to get this. Check that you're going to get this. I'm tired of checking. So, but let's just do it. All right, I'm lazy. I just want to justify again. Just for the person that feel confident when they check their solution. You can always check it. So I'm going to check it. The integral of, I believe it was 2x squared minus x plus 4. And it was being divided by that. Just to verify it. Probably can't work it out. Oh, yes, it does. So here it is. ln a half. Oh my golly. So it's good that we checked it out. See it there? So I made a mistake, clearly. I made a mistake. You might say, well, sir, where did you make a mistake? I made a mistake right here. It's tan inverse. This formula works for, the formula is the integral of a over x squared plus a squared is equal to tan inverse x over a. But there is no 2 in the numerator, so I needed a 2 right here in order to apply this method. So it's good to check your answer. See, it's very good. I'm so happy we checked it. So in order to get the 2 in the numerator, we can put a 2 in the numerator and multiply it by half. Put a 2 in the numerator and multiply it by half. Very good to check your answer. Put a 2 in the numerator, multiply it by half. So minus a half. And then, so now you get a half tan inverse x over 2. So my bad right there. All right, so that is very good. Why we need to use, when you're practicing, of course, all right, and get used to these for the square root of a squared minus x squared. That's cos inverse x over a. All right, so get used to those. For cos inverse and sine inverse, and for tan inverse, we're integrating a over x squared plus a squared, and that's tan inverse x over a. All right, not writing it out, it's all in the notes. All right, easy stuff. All right, so we're finished with integration for 2000. The question is this, another integration. And this integration is asking us to evaluate the integral of e to the 2x over 1 minus e to the 4x. All right. So now what's coming to my mind is substitution. That's the first thing. I'm going to do some substituting. And so I want to look at this as, let me see, I can look at this as the integral of e to the 2x over the square root of, this is now over the square root of 1 minus e to the 4x. How can I write e to the 4x with something as 2x? It's really 1 minus 2x squared. I was looking to see if it's going to be something with sine inverse e. It's really this. All right, dx. So this looks like it can be something with sine inverse of e. And so what I do is call this u. So I'm going to call e to the 2x u. All right, so I'm going to call e to the 2x u. In calling e to the 2x u, then du is going to be equal to, we're going to be 2e to the 2x dx. So that is du. All right, so I need a 2 somewhere up here. I'm going to put a 2 right here and put a 1 over 2 on the outside. All right, so calling all of this I love to call my integrations them I, right? I always say let I. Once I was doing CAPE, everything let I. They're supposed to tire to say let I. So what we're saying now is that I is pretty much equal to a half. I is equal to a half the integral of, the numerator is du, so it's 1 du go here over the square root of 1 minus u squared. Now the integral of 1 minus u squared square rooted is sine inverse of u. This becomes equal to a half sine inverse of u. This is a half sine inverse. This is a half sine inverse of u plus some constant k. Let's call a constant k. But then what is u? What is u? U is, this is now a half sine inverse, and let's plug in what u is. So it's a half sine inverse. Go back to what u is. U was e to the 2x. This is now half sine inverse e to the 2x plus some constant k. Nice and easy, soft with a capital T. Very easy question. Easy, soft. That's what we get. You see how much integration them love ask on the CAPE? Integration is the most important thing on pure math. Let's look at that. One more integration there. All right, so let's do this part now. It says use partial fraction to show that x squared plus 1 over x times x plus 1 all squared is equal to this. So need to use partial fraction to deduce this. So this part is a repeated irreducible quadratic. So what I know in partial fractions is that x to the 4 being divided by x times x squared plus 1, x to the 4 divided by x squared plus 1 all square. I know that this is equal to a over x is equal to a over x plus b over x squared plus 1, b over x squared plus 1, and it's not even b, it's bx plus c over x squared plus 1, and then I need plus, this look like dx plus e over x squared plus 1 all square. That's how we do this question, over x squared plus 1 all square. Now tackling this question, x squared plus 1 all square. All right, and that's because it's an irreducible quadratic. So the first thing is we need our big common LCM. Oh, this is lean, not gonna tolerate that. Let's go with one big LCM. One big LCM is x times x squared plus 1 all square listen to this, all of that into that. That's going to leave us back with our, oh, this was initially x squared, x to the 4 plus 1. All of this is going to leave us back with x to the 4 plus 1. No, look, carefully. This can be a little bit tricky. A lot of persons get confused. X into this going to leave x squared plus 1 all square. So look what I'm going to write this. Look. This is now a. Now x squared plus 1 all square, I'm going to expand it out. And x squared squares x to the 4. Nice. Plus. Now look. Now the second term would be 2x squared. So it's going to be plus 2ax squared. Plus second term square is plus 1 square is 1 times a is a. All right, have to pay keen attention there. So plus, now this into this leaves x times x squared plus 1. And so what we're getting is bx plus c times x squared plus 1. So bx plus c times x squared plus 1. That's a lot of work, to do. But the good thing is dx plus e is just going to be multiplied by x. So the last part is easy. The last part is just going to be dx plus e times x is plus dx squared plus ex plus ex. Now, once you get to this stage now, all right, now we're gonna have to expand this part with the bx plus c times x squared plus 1. Let's simplify that part. I like the color blue. And so x squared, x to the 4 plus 1 is going to be equal to ax to the 4. This must be a lot of marks, because this is a lot of concentration for me. I think this deserves 7 or 8. 8ax to the 4. This is now 2ax squared plus a plus, now I'm going to do it in one go. Bx times, this is really x squared plus x. Look at all of this as x squared plus x. Because x times x squared plus 1, now I'm going to replace that with x squared plus x. All right, think of all of that as x squared plus x. So instead of think of it, let me let you see it. You're going to see x squared plus x. It makes it easier to do it in one go. So we have bx times x squared is bx cubed, bx cubed, bx cubed, bx times x squared is bx cubed, bx times x is bx squared. It's now bx squared. And then c times x squared is now cx squared. Plus c times x is just cx. Plus bx squared plus ex. All right, now the next thing we're going to do is equate coefficients of x to the fourth. So we have x to the 4 right here, and we only have 1 x to the 4 here. So what we can conclude then is that 1 is equal to a. So a equal 1, so we're good. We'll govern. Now there's no x cubed term over here, and so what we can conclude is 0 is equal to, the x cubed term over here is b, and so 0 is equal to b. Yeah, b is the only x cubed term. Then we need to look at our x squared term. For the x squared term, we're going to have 0 is equal to 2a. That's one x squared term. The next x squared term is b. It's 2a plus b plus c plus a whole of d plus d. Right? So that's 0. But then again, we know a and b. And so what we can conclude is 0 is equal to a is 1. And this is 2. 0 is 2 plus c plus d. So that's 0. That's when we equated our x squared term. So let's try to equate x terms now. There is absolutely no x here. And so 0 is equal to, equating our x terms, we have cx plus ex. So 0 is equal to c plus e. 0 is absolutely equal to c plus e. Since 0 is equal to c plus e, we're nice. And then what do we know? We know that the constant 1 is equal to the constant on our right-hand side, which is a. And we already found that 1 was a, so that doesn't give us any new information. So what do we know? From the 5 equations, we know a, we know b. Now we need to find c. So we have 5 equations, and we have 5 unknowns, but we know 3 already, so we're left with 3 equations. The 3 equations we're left with is, well, actually we have 2 plus cd equals 0, and c plus e is equal to 0. So now, if c plus e is equal to 0, then c is equal to negative e. So c is equal to negative e. That's one thing we can conclude. So straight away, we know that c is equal to negative e. From right here, c is equal to negative e. C equal negative e. Now, we have some issues because now we're looking at 2 equations, but we still have 3 unknowns. We still have 3 unknowns. So what are we going to do? Let's see what are we going to do. How are we going to find d? How are we going to find d? So let's go back now and look through it. X to the 4, this is ax to the 4, so indeed 1 is a. 0x cubed is b, and so 0 equal b. And let's go back one more time again. So with the x terms now we have, with the x squared terms we have 2a plus b plus c plus d. And we know a and b is 1, so we get 2 plus c plus d, and that's 0. Then we go to our x terms, which is, for x terms, we almost can't find the x term. X term we're finding is cx plus e. For x terms we're finding is 0 is equal to c plus e. 0 is equal to c plus e. And so what they're telling you is c and e equal 0. So c is equal to 0 and e is equal to 0. So from right here, c is equal to e and they're equal to 0. So we'll add them, we're just going to get 0. So c equal e, which equals 0. And then now, when we get c here so to be 0, then 0 is equal to 2 plus b. 0 is equal to 2 plus b. And so what we're getting is 0 minus 2 is equal to d. 0 minus 2 is equal to d. And so negative 2 is what d equal to. D equal negative 2. So now we're nice. We'll find a, we'll find b, we'll find c, we'll find d, we'll find e. So let's erase now. So a we found is 1. A is 1. B we found is 0. So this is plus 0x. B we found is 0x. C we found is 0. D we found is negative 2. And E we found is 0. And everything works out now. Everything works out fine. We found A to be 1, so we get 1 over x plus B, which is 0x plus 0. But 0 over anything is 0. Then we get plus. And then we can actually, don't have to put plus because D is negative 2. So it becomes minus 2 so it becomes minus 2x plus 0. Nice. So that's what we get now. Nice, nice, nice. So all of this is just the same as right here. All you have to do now is to just show that this now, all of this can go away. And so all of this, it works out to just be equal to. So if we call this j, just to call this j, so what we're pretty much saying now is that j is equal to 1 over x. And then looking at it, it's 1 over x minus 2x over x plus 1 all squared. I will do it. Question nice and easy. Soft with a capital T. So x squared plus 1 all squared. Soft with a capital T. Easy. Nice. Let's look at the integration now. So to bounce off this integration now, it says hence determine that. When it says hence, it means you have to use it. Notice it didn't say otherwise. Hence mean you have to use what they had given you. That's what hence mean. Hence mean you have to, but most you have to do it. Don't do nothing else. You have to do that way you and done. All right, so that's what hence mean. You have to utilize that way. Have to. All right, so many persons have to do another method. When they say hence, they mean afi. They mean afi, you have to do it, you have to do it, you have to do it. All right, So 4, so I have to emphasize it over and over and over. So x to the 4, then x times x squared plus 1. We're just writing back the partial fraction. We know that this, we found that this was equal to 1 over x minus 2x over x squared plus 1 all squared. So that's what we did know. We did know this. And so now we are going to find the integral of this, and the integral of this is equal to the integral of this minus the integral of this. That's why it's a hence, meaning using this. And so the integral of this is equal to the integral of 1 over x is ln. I like to put my modulus. It's minus ln the modulus of x, just to show respect to ln x, because we cannot take log of a negative number. Minus, now the differential of the denominator is in the numerator. Differential of x squared plus 1 is 2x. And so if I were to call this u, if u is equal to x squared plus 1 all squared, then this would be du. So it's u squared. I'm integrating 1 over u squared, and that becomes u to the minus 1 over minus 1. So this becomes plus. I'm doing it visually, guys. I'm going to write it down, of course. Doing it visually. All right, let's not do it visually. I can see it, but just to write it down so we all see what I'm doing. For this part right here, I'm going to write it in black. I'm calling u x squared plus 1. That's u. If u is x squared plus 1, then du is equal to 2x dx. That's du, 2x dx. All right, du is 2x dx. Now, once we get that now, we're going to get minus, now the integral of 2x over x squared plus 1 all squared. All right, we're substituting 2x dx as du, and x squared plus 1 all squared is now u squared. So it's minus the integral of 1 over u squared du. Then when we integrate 1 over u squared du, that's like integrating u to the minus 2. So integrating u to the minus 2, you're going to get minus, integrating u to the minus 2, you get u to the minus 1 divided by negative 1 plus some constant of integration c. Now, never you done it this so. All right, you're going to have to re-substitute back what you had put in for u. So what did you put in for u? This is just going to then become ln the modulus of x, and then minus and minus become plus. They become plus. U to the minus 1 is 1 over u. 1 over, but what was u? I recall that u was x squared plus 1. So it becomes plus 1 over x squared plus 1 plus your constant of integration plus c. All right. That is that question. Easy, soft, easy 5 marks or so. 4, yeah, makes sense. Wouldn't be 5 because this was a little too easy. Soft. All right, that was that. And that's it for the integration. We're back to sequence and series.